All right, we're here for part two. We're going to start off with our first example using the Clapeyron equation from the previous page. That equation looks like this. We have the natural log of P2 over P1, and that equals the negative delta H VAP divided by R 1 over T2 minus 1 over T1. And what this does, of course, is it relates the vapor pressure at a certain temperature with its vapor pressure at a different temperature for some liquid. And in order to do this, we need to know what the heat of vaporization is, or the enthalpy of vaporization, which is given there. So the first thing we want to do is identify what P1, P2, T1, and T2 are, all of our variables here. So we have our P1 and our P2, we have our T1 and our T2. Our P1 and P2 we can use as the normal boiling point of benzene. So that is a pressure of 1.00 atmospheres. And this comes at its normal boiling point of 353.3 Kelvin. We're asked to calculate now the boiling temperature if we reduce the temperature. We know it's reducing the temperature because it's reducing the pressure, but we're not told what that temperature is. So this is our variable. This is what we are asked to solve. For P2, this is going to be equal to 5.00 kilopascals. You see we have an issue right away in that our two pressures are in different units, so we want them to be in the same units so that we can use them together in the equation. So let's change our P1 from atmospheres to kilopascals. 1 atmosphere is 101.3 kilopascals, and then we're good to go. And our delta H VAP is our only other unknown, which is given in the question. So we can start to fill our values in here now. We have our natural log of P2 is 5.00 kilopascals divided by our P1. That is going to be equal to negative delta H VAP, which is 3800 joules per k mole. No, it's not joules per k mole. It is joules per mole. It's our R that's in joules per k mole, which is 8.314 joules per k mole. 1 over T2, which is our big unknown, minus 1 over 353.3 Kelvin. So we can compute everything on the left, and that actually turns out to negative 3.008. This is unitless. These kilopascals go, and the natural log of those numbers is a unitless negative 3.008. And what we can do now is we can bring this piece over to the left-hand side, because those are just values as well. And we're going to say negative 8.314 joules per k mole divided by and we can calculate this 1 over 353.3 Kelvin as well. That's equal to 0.002830 k to the minus 1. Just notice here too that I've been typically keeping sort of one more significant figure than I ought to be. Usually that's what I do, is keep one extra sig fig and then round it to the correct number at the very end. All right, let's continue our work here. So everything on the left-hand side here becomes 0.0008120 k to the minus 1, because all the units cancel except for degrees Kelvin. 1 over T2 minus 0.002830 k to the minus 1. We can add 0.002830 Kelvin to both sides. That gives us 1 over T2 equals 0.003642 k to the minus 1. Take the reciprocal of both sides, and we get T2 equals 274.6 Kelvin. You round that to 3 significant digits, that's going to be basically 275 Kelvin. And that's the answer that we are looking for. That is going to be the boiling temperature of benzene when it's at a pressure of only 5 kilopascals at very reduced pressure. All right, so coming back, the next topic we're going to be talking about is phase diagrams. And phase diagrams are basically two-dimensional drawings which show for a given substance what phases it will exist at different temperatures and different pressures. We know both temperature and pressure play a role in determining what phase something will be at. We know that most gases, for example, if you increase the pressure enough, you can compress the gas typically into a liquid or sometimes even a solid. We know that melting points between liquids and solids, those phase boundaries depend on the temperature as well. So we have a couple of different phase changes depicted here. This one would be melting. This would be going from a solid to a liquid. You could have evaporation, which is liquid going into a gas. And the one that you're seeing here is actually sublimation. This is dry ice going directly from the solid into the gas. And the reverse process is called deposition. So the phase diagram basically shows what all these boundaries are and how they depend on temperature and pressure. They look more or less something like this, where we have a two-dimensional graph where we have pressure here on one axis, temperature on the other axis, and these lines that you see represent a set of temperatures and pressures where there will be an equilibrium between two phases. In other words, it's the boundary between two phases. So the idea is if you were, say, at a given pressure, let's say you were at a pressure right here, anywhere kind of in this region, here of temperature and pressure, that substance is going to exist as a solid. So the idea is if you increase the temperature and keep pressure constant, you're going to be following this line this way. Eventually you'll hit that line there. When you hit that line, that means at that temperature, if you look at the temperature where that hits, that's going to be the temperature where this is going to be melting at that temperature. So if you cross that line, you go into the liquid phase. So at all temperatures and pressures in this zone, defined by these boundaries here, these are all going to be liquids. Finally, typically at higher temperatures and lower pressures, that's going to be over in this part. These are all gases. And one interesting thing you can see here is a point right there where all the lines meet. This is called the triple point. And at the triple point, what happens is you have an equilibrium existing between solids, liquids, and gases all at once. All right, so this is just showing more or less the same thing. The line is the boundary between two adjacent phases. If you're on the line, it means you're in an equilibrium situation. So between a solid and a liquid, you can imagine an equilibrium situation is kind of looking like a glass with ice cubes in it and water at 0 degrees Celsius. You have an equilibrium going on between solid and liquid together at the same time. You have both phases present. That would be a point on the solid-liquid line. The critical point is an interesting point as well. You can see that this happens typically at high pressures and high temperatures. The critical point is a point at which above that, at higher pressures and higher temperatures, there's no boundary anymore between liquids and gases. And what happens if you're above the critical temperature and above the critical pressure, you are in a sort of a intermediate phase, which is called a supercritical fluid. And supercritical fluids are actually extremely useful. Supercritical fluids are, and you can see here, it's kind of fuzzy, the difference between liquids and gases at this point. You can kind of think of a supercritical fluid as being like clusters of molecules that are separated from other clusters by large distances. So since you have certain molecules that are clustered together, it has some liquid-like properties, and because there's large different distances between clusters, it has gas-like properties as well. You can see an image of this right here, where you have a liquid and a gas together, and you're looking through a little window at the boundary between the two phases. And then what happens is if you start to increase the pressure and increase the temperature, you can start to see a transition to eventually a sort of a single phase that we call a supercritical fluid. All right. So with a supercritical fluid, these are actually used industrially for several processes. Supercritical fluids are often really good at dissolving things because of the high pressure and temperature. And in particular, carbon dioxide has quite accessible critical temperatures and pressures. And so supercritical fluids, supercritical carbon dioxide is often used to decaffeinate coffee beans. So if you take coffee beans, expose them to high pressures and temperatures of CO2, the caffeine and some other flavor compounds as well will dissolve out of the beans, go into the supercritical fluid, and then simply by releasing the pressure, what will happen is the supercritical fluid will go back into gas phase CO2. Gas phase CO2 has no capacity to dissolve caffeine, and the caffeine will come out of the fluid almost like snow. So solid will form and fall out. Obviously, that's good for two reasons. First of all, you can make decaf coffee, and then you could sell decaf. It's often why decaf doesn't quite taste as good either, because some of the flavor compounds come out with it. But you can then take the caffeine isolated this way, purify it, and it's often added to soft drinks like Pepsi or energy drinks or things like that. So here's another example. It's looking at the phase diagram of a hypothetical substance called Bogus Im, which is not a real thing. And you can see here a couple of points. First thing says, does Bogus Im have a lower or higher density than in the solid phase than in the liquid phase? So if you look at our diagram, typically at low temperatures and high pressures, this is where things exist as a solid. At high temperatures, low pressures, that's where things exist as gases, and intermediate is where they exist as liquids. So does the solid have a higher or lower density than the liquid? So imagine you're at a certain point right there. What happens if you increase the pressure on that liquid? You'll start to compress the liquid. You're going vertically up. You're keeping the temperature constant. You'll hit this line where you're at equilibrium between the solid and the liquid. And if you keep going, you go into the solid phase. So what this suggests that if you pressurize this liquid, you can convert it into a solid. If that's the case, if you're pressurizing something, you're pressurizing a liquid that goes into a solid, the solid must have a higher density than the liquid because you're compressing it. Some substances, it's very rare, but some substances, including water, have a different looking phase diagram that looks like this. It's kind of exaggerated a bit. This is solid, liquid, and gas, where if you're at a liquid here and you increase the pressure, you don't go into the solid phase. In fact, if you start in the solid phase, you can compress it and go into the liquid phase. So this is the case with water. If you have solid water, which we call ice, and you pressurize it, you can convert the solid into an actual liquid. So that's the answer to A. It's going to have a higher density. Is the triple point for Bogus Im at a lower or higher temperature than its normal melting point? So this is the triple point. Its normal melting point is going to be the temperature at which it converts from a solid to a liquid, or that those two phases are at equilibrium at 1 atmosphere, which is the same as 760 torr. So that's at this point right there, right? That is going to be Tm, that's the melting point. This here is Tb, that's the boiling point. So the question is saying, is the triple point, which is here, at a higher or lower temperature? Well, because it's more this way, this is lower, this is higher. So the triple point is going to be at a lower temperature. C, explain the phase changes that occur as you go from point C to D. Well, you're going from a solid phase here into the gas phase here, and you cross one phase change right there. You go directly from the solid directly into the gas. So that would be sublimation. So basically you skip the liquid phase going that way. What point represents the triple point of BO? That's up here. Notice that line, that gas-liquid barrier line, stops at point B, doesn't continue on. So that means if you're sort of above this point, you're at a supercritical fluid up here. Here's a phase diagram showing different allotropes of sulfur. So sometimes you can have phase diagrams that are a bit more complicated than those three-phase ones that we just took a look at. This looks something similar, at high temperature, low pressure. You're in the vapor or gas phase. Here you're in the solid phase at higher pressures, lower temperatures, and liquids is intermediate. But what we see here is there's sort of two different solid phases for sulfur. We have, they're two different crystal structures. They're both pure sulfur, but they are two different solids, and they will exist, I guess, in equilibrium along that phase line right there, those temperatures and pressures, although it would probably take a long time for equilibrium to be established if you suddenly put a system like that under that kind of pressure. Just an interesting picture here. This is showing a spot in New Zealand where you have a lot of monoclinic sulfur that is being emitted from hot springs. And you can see the bright yellow color here. That's very characteristic of sulfur. Ice as well, or water, has a much more complicated phase diagram than we necessarily usually look at. If you take ice and you compress it to very, very high pressures, so we're looking at in this diagram here pressures in thousands of bars. Remember that atmospheric pressure is around 1 bar, so these are extremely high pressures, not pressures we ordinarily experience, but we do know that ice takes on a number of different crystalline forms that you can see in this picture. And we have names for these: ice 1, ice 2, ice 3, ice 4, and so on. Geology, these phase diagrams showing different phases or different polymorphs of solids becomes quite important because you can have very long times on the geological timescale. You can often have very high pressures if it's underground, and often have high temperatures as well. So you can have a lot of interesting chemical changes taking place on those sorts of scales that we don't often see in the chemistry lab. So here's just a close-up of the phase diagram of water, and I indicated before how water is a bit unusual because its solid-liquid phase boundary, or it's not really a boundary, it's more the set of pressures and temperatures where solid and liquid is in equilibrium. I said this one is a bit unusual because from the triple point it veers off to the left or towards lower temperatures. And this is a very unusual property of liquids or of any substance. Most substances, this line will go off to the right, but in water it doesn't. It goes off to the left. This means that solid water has a lower density than liquid water. Water is most dense when it's at 4 degrees Celsius, or actually I think 3.8 degrees Celsius, which is about the temperature of your fridge. This is actually important for life on Earth because it means that water, when it's in its frozen state, when it's ice, will float to the top. And so if you have a lake, rather than water freezing and then sinking to the bottom, like it would if the lake was filled with almost any other substance, it floats to the top. It forms a hard layer of ice on top, which allows us to, go skating, I guess, but it also insulates the bottom part of the lake from the outside air, so it prevents the lakes from sort of freezing all the way through, which is fantastic news if you are a fish. So the normal boiling point of water is 100 degrees Celsius when the external pressure is 1 atmosphere. If you take water and you were to increase the pressure, so let's say you put water into a pressure cooker and you increase the external pressure by, pressurizing the container from 1 atmosphere to 2 atmospheres, using the Clausius-Clapeyron equation, you could calculate the new boiling point, which turns out to be 121 degrees Celsius. And this is kind of codified in these pictures. If we look at 1 atmosphere, the boiling point being right here, 373 Kelvin or 100 degrees Celsius. If you increase the pressure, somewhere up here like 2 atmospheres, basically what we're doing is we're going up 2 atmospheres and we go to a new temperature up here, which would be 121 degrees Celsius. Or I guess that's equal to 494 Kelvin. And so this diagram kind of shows the relationship between the boiling point and the pressure. And you could, at any point along this line, determine what the boiling point of the substance would be at any of those pressures. If you reduce the pressure, if you go down to say, 0.3 atmospheres, that would be like decreasing the pressure down this way, and that would of course bring your temperature over to the left, which would be at a much lower temperature, which is 69 degrees Celsius, which is again much colder than the regular boiling point of 100 degrees Celsius. So there you go. If you're ever on the top of Mount Everest and you're trying to boil water, you don't have to heat it up very high. It actually would be very difficult to cook your craft dinner up there because it would take a long time because the temperature is not the regular boiling temperature of water. It wouldn't take you very long to reach that temperature, but once you're there, it wouldn't be able to cook your food as quick. Okay, I think we're going to take a break now and stop the video, and then we'll pick it up again. We'll do another part.